So welcome everyone. I'm going to be reviewing solutions for the Regents next Tuesday. So let's get started. A solution is a homogeneous mixture of two or more substances in the same physical state. Usually that's a liquid or a gas. A solute is a substance that is dissolved, and the solvent is what's dissolving the solute. And normally we use water because it's such a common solvent and it's really good at dissolving things. So when you see AQ written in a chemical equation, remember that means that it's a water solution. Solutions can be described as being unsaturated, meaning it's not full yet, you can add more. Saturated, it's holding the maximum amount, and supersaturated, it's holding more than it's supposed to. And they're unstable, so if it's shaken, if you drop a crystal in, a piece of dust, that could be enough to actually make it solidify. So one way to know if you have an unsaturated, saturated, or supersaturated solution is to just drop a little bit more solute in there. And if it dissolves, you know it's unsaturated. If it settles to the bottom, then it's saturated. And if it turns into a solid, then it was supersaturated. And a good example of this would be the hot ice demo, which you can see here. So by dropping a little crystal in there, it's actually going to cause it to form a solid. And this is oftentimes used in hand warmers because when it solidifies, it releases heat. So that's a good example of a supersaturated solution. Properties of a solution, they're homogeneous mixtures, meaning that the concentration is the same throughout. Solutions are clear and light will pass through them, so you can test by shining a flashlight through it. They can be colored, like when you add food coloring to water, and it will not settle if left standing, which means if you let it sit for a while, you're not going to get crystals falling to the bottom unless water is evaporating out. And it will pass through a filter, so you cannot separate the two by filtering it. You'd have to either distill it or boil the solvent off in order to get the solute back. Unless it's like alcohol and water, because alcohol has a much lower boiling point. The alcohol will come out first and the water will come out second. Factors that affect the solubility are the polarity of the solute and solvent. Polar solvents only dissolve ionic compounds and other polar solutes. Nonpolar dissolves nonpolar. So remember, like dissolves like. And as the temperature goes up, the solubility of most things increases with the exception of gases, which become less soluble as the temperature goes up, which is why your soda goes flat a lot faster when it's hot out instead of when it's cold. And pressure, as it's treated on the Regents, pretty much affects gases only. So you can make gases more soluble by increasing the pressure. When the pressure gets lower, the gases come out of solution. And that's when you open the soda bottle, that noise you hear is the gas escaping because you're decreasing the pressure. Gas is actually produced at high temperatures, low temperatures and high pressures. And then looking at table G, it shows a lot of useful information here. Things to pay attention to is how much is soluble in 100 grams of water, which is the same thing as 100 milliliters. Because 1 gram of water is the same as 1 milliliter. And then the bottom you have the temperature in Celsius. Things to note are the gases curved down. So on table G, you actually have three gases: ammonia, HCl, and sulfur dioxide. The other stuff, as the temperature goes up, they become more soluble. So what you would do with this is either match up the temperature with the substance to figure out the maximum amount that can dissolve to make it saturated, or you could tell if it was unsaturated if it doesn't go all the way up to the line. So if you get a point below the line, that means it's unsaturated. And if it's on the line, it's saturated. And if it's above the line, it'd be supersaturated. Other things you want to watch out for is if you're using an amount of water different than 100 grams, like 75 grams or 200 grams, you'd have to change your answer accordingly. And be very careful when you're dealing with these substances down towards the bottom, because all the lines get jumbled together and you got to make sure you have the correct one. So as example, how much sodium chloride will dissolve in 100 grams of water to form a saturated solution at 30 degrees Celsius? So you start by going to 30, and then you go up till you hit the line for sodium chloride, which is this one right here. And one of the things to notice about sodium chloride is it becomes more soluble as temperature goes up, but not as much as the other substances. So anyway, at 30 degrees, you can dissolve about 38 grams. And normally they give you a range of plus or minus 1 or 2. So if it was plus or minus 1, you take an answer from 37 to 39. If it's plus or minus 2, then it would be from 36 to 40. And in this example, we're using an amount that's not 100, we're using 300 grams. So we need to know how much will dissolve when it's 60 degrees, keeping in mind that's only 100 grams of water. So starting at 60, coming up to here, you can hit 46 grams of potassium chloride and 100 grams of water. And they want to know how much is going to dissolve in 300 grams of water. So usually if you set it up as a proportion, you'll get the right answer every time. But if you notice that it's 3 times as much water, you just have to multiply the 46 times 3. So that's 138 grams. Now, another chart that's very useful for solutions is table F. And there's some very important terms on table F. You have soluble, which means that it will dissolve in the solvent, and the solvent is water. If it's insoluble, it either has a very, very low soluble or it won't dissolve at all. And if it's insoluble, it will form a precipitate that will usually fall to the bottom. But it might stay in solution for a while before it actually does. So an example would be silver nitrate mixed with a sodium chloride solution. You get a double replacement that makes sodium nitrate and silver chloride. And the silver chloride is all this white stuff you see in the test tube. So looking at table F, you can see over here on the left, there's everything that's soluble ions. And if it's an exception, it's insoluble. So all your group 1 ions are always soluble: ammonium, nitrate, acetate, hydrogen carbonate. and chlorate, always soluble. It doesn't matter what you pair it with. But the halides, chlorine, bromine, iodine ions, they will form a precipitate when they combine with silver, lead +2, or dimercury. Because remember that this is a polyatomic ion on table E. And same thing is true for the sulfates. They will combine with silver, calcium, strontium, barium, and lead +2 to make an insoluble substance. Over here on the right are the insoluble compounds, and any exceptions make it soluble. So if you pair carbonate with ammonium, for example, it will dissolve in a solution, which if you notice over here has no exceptions. And I find just by drawing a box around it, and then just a little mnemonic is if it's in the box, it's insoluble. But I know some other people draw a funnel. Because if you were to filter this, anything that's in the funnel is going to get trapped in the funnel in the filter paper, and the rest of it will go through. And then colligative properties refers to the changing the boiling point, the freezing point, and the vapor pressure of a compound when you dissolve a solute in it. So the freezing point is going to go down, the boiling point will go up, and the vapor pressure will decrease. And it's referred to as freezing point depression, vapor pressure depression, boiling point elevation. And a good example is how you make ice cream. You have ice and salt, and you mix that together, it makes it colder and causes the milk to freeze. Because milk doesn't freeze at 0 degrees like water does, it freezes at -12 degrees Celsius. So the amount of the temperature change is going to depend on the amount of stuff that you get into solution. So you got to check and make sure it's actually going to be soluble. So the example here would be glucose. If you dissolve that in water, you're going to get a 1-to-1. 1 mole of glucose will make 1 mole of glucose in solution. But if you dissolve sodium chloride, 1 mole of sodium chloride will end up producing 2 moles of ions. So because you get twice as much stuff, it's going to lower the temperature twice as much. So when it comes to colligative properties, it really doesn't have to do with what the stuff is. It's just how much of it there is. So the example here is dealing with boiling point, and they want to know which one's going to have the highest boiling point. So first you would look at the concentration and hopefully notice that it's all the same. So then you have to start thinking about what's going to happen to these ions when you put them into solution. Potassium chloride is going to make 2 ions. And potassium sulfate will make 3 ions. And potassium phosphate will make 4 ions. Whereas potassium nitrate is going to make 2 ions. So it's really important you notice the polyatomic ions and their charges. So because potassium phosphate produces 4 ions compared to the other ones, it's going to raise the boiling point the most. And if you were to put this in ice, it would lower the freezing point more than the rest of them. And then molarity and parts per million are ways to measure the concentration of solute in the solvent. So molarity is equal to the moles of solute per liter of solution. And you have to be very careful to make sure that you express the volume in liters. So if it's given to you in liters, you're good to go. But if it's given in milliliters, you're going to have to remember to convert to liters. So remember that 1,000 milliliters is equal to 1 liter. So easiest thing to do is just to move the decimal 3 places to the left if it's in milliliters to put it in liters. So in this question, it says, what is the molarity of a solution if 25 grams of sodium hydroxide is dissolved in 100 milliliters of water? So remember that you need moles per liter. So you need to first convert the mass into moles. So you use the mole calculation, which is the given mass over the gram formula mass. And the gram formula mass of sodium hydroxide is 23 grams for sodium, 16 grams for oxygen, and 1 gram for hydrogen, which gives me a total mass of 40 grams per mole. And the volume is 100 milliliters, which is equal to 0.10 liters. So getting back to this, I got to plug it into this equation now. So moles is 25 grams divided by 40 grams per mole, which gives me 0.625 moles. So now that I got the volume in liters and I have the moles of solute, I can plug it into the equation and get the answer. So 0.625 moles divided by 0.1 liters gives me a concentration of 6.25 molar solution. And finally, parts per million is another way to express concentration. And normally we measure it when there's very little solute per mass of solution. So we're just trying to make a really, really small number a little bit bigger and easier to handle. And so you calculate it by taking the grams of solute divided by the grams of solution. So say they give you the mass of the solvent, you have to remember to add that to the mass of the solute to get the mass of the solution. And then you multiply by 1,000,000. So that's used for things like concentration of carbon dioxide in the atmosphere, which has passed 400 parts per million for the first time in recorded history and stayed above that level. And if it's something that's really bad and much smaller concentrations, you might actually use parts per billion. Like lead is actually measured in parts per billion because 15 parts per billion is considered to be too high. And in Flint, Michigan, they had an issue with the public water having levels higher than that. So here's an example. Let's calculate the total mass of lithium bromide required to make a 500 gram of an aqueous solution of lithium bromide that has a concentration of 388 parts per million. Your response must include both the correct numerical setup and calculated result. So make sure you answer both parts of the question. So just taking an inventory of what we have, parts per million is 388 grams, ppm. The mass of the solute, which is a lithium bromide, is what I'm actually looking for because it says calculate the total mass of lithium bromide. And the mass of the solution is 500 grams. So plugging all that into the equation, mass of solute, and then mass of solution, and multiply by 1,000,000. So you get 388, excuse me, parts per million is equal to X times a million, which you can do. Makes your life a lot easier because you remember 1,000,000 over 1 is the same thing as multiplying by 1,000,000. So you multiply the two fractions. And having it set up like this, you can put the 388 parts per million over 1 and then cross multiply. And you get X times a million and when you multiply 388 times 500, you get 194,000 grams times parts per million. Keep in mind that when you divide both sides by 1,000,000, you're going to make that parts per million go away. Because that's what you're measuring, is how many parts per million. And so for this, you get 0.194 grams of lithium bromide is what you would need to make the solution. So that about covers everything that you need to know for solutions. And hopefully you find everything useful when you study for the Regents on Tuesday. So thank you for joining me.